With rising healthcare costs and an aging population, remote health monitoring and wellness management will be a large market sector in the Internet of Things. In this demo, we will show how Cubicon automates message passing using a simple telehealth system of a patient being monitored at regular intervals by his doctor. Our patient's smartwatch sends raw pulse streams to his smartphone. The smartphone processes the streams into heart rate and blood pressure readings. The readings are transmitted to a clinic that logs the data. If an exception occurs, the doctor's tablet will alert him of the event. Our patient has given an organization permission to harvest his data for a research project. A CubeWeb-enabled device is used as a base station to monitor and control things over low-power wireless networks called a constellation. A constellation is a form of personal area network. The patient's constellation includes 5 devices. However, in this example, we will focus solely on the smartphone as base station and smartwatch that will take readings. Typical requirements of a PAN environment include signal processing, distribution of logic, real-time interaction, protocol conversion, and analytics. What Cubicon brings to the table is a common development environment to create and maintain this high level of sophisticated functionality across thousands of OEMs. In the following frames, we will show how Cubicon formalizes different abstraction levels of a system, providing a common way for developers to visualize complex nested relationships. We start out with a domain. A domain is a form of virtual private network. In this example, a person's domain is depicted in light blue, a company's in green, and an organization's in yellow. A device is a node in CubeWeb, identified by a Cubicon globally typed identifier, GTI, and IPv6 address. A low-power thing is a subnode in CubeWeb, identified by a Cubicon globally typed identifier and optionally an IPv6 address. In this example, devices and things are displayed in peach. CubeEngine is a type of embedded hypervisor. It will provide a common operating environment across thousands of device types that will populate the IoT. In this example, CubeEngines are displayed in blue. Each CubeEngine will supervise one or more Cubicon virtual machines. In this example, virtual machines are displayed in dark green. Things with limited resources can be embedded with a Cubicon VM, replacing the need for legacy real-time operating systems. In this example, a VM is designated as a base station to drive the patient's low-power network. A module is the smallest piece of Cubicon software. One or more modules make up an app. Prior to download, the software repository distills each module into a grove. To be clear, a module is considered a design abstraction and a grove a runtime abstraction. This separation brings a new level of clarity to representing complex systems. There are 2 kinds of groves, transaction and real-time. Both are depicted in light green. A transaction grove processes memory that is shared. A real-time grove processes memory in isolation. A grove contains objects made up of structures and behaviors. In this demo, objects are displayed in white. Objects may be linked for the purpose of message passing. During execution, an operation or equation will use messages to access slot values in objects located in the same grove or located in a different grove in another VM, device, or domain. In our example, the smartwatch's object is responsible for collecting the patient's pulse stream as data that will be processed in the smartphone. Remote processing offloads processing from the resource-constrained thing to the device. In CubeWeb, there are 8 types of information exchanges, each performed over its own Cube protocol. Exchanges internal to a domain are performed as an exchange. Exchanges external to a domain are performed as a service. Mechanisms are in place if the patient, clinic, doctor, or research institution wishes to set a fee for the information being exchanged. In this demo, we'll focus solely on the information exchange type, message. A message token is used to read, pull, or write, push data values in a message. In this depiction, we see a message token pushing the value from the average heart rate attribute slot to the heart rate status attribute slot, which then returns an acknowledgement of receipt. This exercise completes the object-to-object messaging example. There are 2 types of message tokens, read and write. Messages can be exchanged between objects located in one device or any 2 network devices running a Cube engine. The color of a slot designates its type. A message token's color will correspond with a particular slot type. As the name implies, a read message token will read an attribute or function slot located in another object. A write message token will write to a procedure slot located in another object. Messages are processed either asynchronously or synchronously. To maintain a real-time Grove's internal synchronous behavior, all external messages are performed asynchronously. In a real-time Grove, messages are processed in epochs. An epoch can be measured in milliseconds or microseconds. When an asynchronous message is sent, a callback method will continually check the queue for a response. This frame depicts control flow threads in 2 different Groves. Black is used to depict the control flow step being executed. You cannot send a write message to a real-time Grove because it breaks the semantics of the Cubicon language model. Constraints such as this automate processes typically performed by the developer, allowing a much larger population to program complex real-time systems. In a transaction Grove, messages are processed in parallel. To maintain a transaction Grove's internal asynchronous behavior, all external messages are performed synchronously. A synchronous message takes a lock on one or more objects. Objects must commit before a write action is completed. For the remainder of the demo, foobar A and B will replace example names. Now let's look at the behavior window in the IDE. Before we start, we would like to point out that the IDE should be considered a wireframe that professional UI engineers will modernize. The behavior window is used to depict a system's behavior from 3 perspectives: process flow, control flow, and state. However, this demo will discuss control flow. We will start the process of declaring a message by opening the control flow behavior called accessor method slot. One click will display its operation and equation icons. This particular method is made up of icons that represent 6 operations and equation steps. Each icon's color maps to a step type depicted in buttons across the top of the window. To begin the process of declaring a new transfer operation, we click the Transfer button. This operation will use a message to read a value located in another object. There are 6 transfer operations in the Cubicon language viewed in the Create Transfer pop-up pane. Each field was designated to help developers visualize the flow of data between slots. In this example, we will focus exclusively on the 1.0 arm. It is used to read a source value from a remote object or write a destination value to a remote object. To create the operation, we click the 1.0 arm transfer field. Characteristics of the newly created transfer operation will appear in the Transfer 1.0 arm pane. The operation will also appear as an icon in the operation equation step tray on the bottom of the control flow schema pane. Required fields appear in green. Once selected, they are bordered in red. Note how easily the action field is toggled from read to write. Fields change orientation between read and write actions to keep the destination slot on the left. To create the message, we select the message field that opens up the message pane. The message pane depicts a library of declared messages for each module. The developer can choose to use a declared message or create a new one. We will now click on the message object B to verify whether it's fit for purpose. The characteristics of message can now be viewed. To bind the message to our transfer operation, we simply click the Bind button. We will now go through the process of binding a source data slot to our operation. To begin, we click on the number B slot in the object structure list. During the binding process, the IDE will constrain the list to only display eligible slots. We click Source Data Slot number B to bind it to our transfer operation. To complete the process, we select Destination Data Slot number A to bind it to our transfer operation. The transfer operation is now complete. In the actual IDE, the operation would be ready for simulation using default characteristics. We click the Control button in the transfer pane to commit the new operation to a designated software repository. The transfer operations pane depicts source and destination data slots so the developer can see how the data structures will be traversed. In this frame, we will go into edit mode to place our completed transfer operation into the method. We begin by clicking the Edit Method field. We select the transfer operation icon in the operation equation step tray. The transfer operation icon is placed into a control flow schema. We click control flow arrow to instruct the IDE where to insert the icon. The IDE prohibits the icon's placement in any location that would break the semantics of the current control flow schema. The control flow schema is automatically reconfigured to accommodate the moved operation icon. We will now leave the edit method mode. In a method, icons and arrows are used to express branching. A logic flip is performed by simply toggling the yes/no symbol on the icon, a much simpler process than traditional cut and paste code refactoring. In this series, we will be discussing icon labels located on top of the icons. The labels are a concatenation of the first letter of slot names contained in the icon. For example, the letters BI for Bank ID slot. Labels are automatically generated and maintained by the IDE. A click on the label button gives the developer 7 other views such as step number, GTI, or the option of removing the labels altogether. Note the icon labels now reflect the last 3 digits of the GTI to assist with pattern matching. We will now click on the method's GTI HID 345 to open up its software component identifier pane. Cubicon was designed to automate the process of software development. The use of automation and visualization in the Cubicon IDE will enlarge a population able to create and maintain complex systems such as those demonstrated here. Cubicon is a common framework to support the interaction of billions of unattended devices and things.